Hello, today I'm here to talk to you about Undo's time travel debug for Java integrated into the IntelliJ IDE. I have an example of an application here that is known to catch an exception and exit. As we know this application will exit following an exception, we have a breakpoint set on line 27. So let's start debugging it. As you can see, we have stopped at the breakpoint and the exception has been output to the console by the previous line. We can see from the debugger that the exception is the concurrent modification exception that we were expecting. Let's set an exception breakpoint on the concurrent modification exception to stop execution where the exception was thrown. Normally, you would have to restart the application at this point, but with time travel debugging, we have a complete recording of the application's execution, which we can replay backwards and forwards in order to explore what happened. In order to control this replay, there are some additional buttons added to the UI, including the reverse step over, reverse step into, and reverse step out, which offer reverse equivalents of the usual stepping operations. Additionally, there is a resume back button, which, like the resume program button, resumes the execution only in reverse. Let's use this button to run the execution back to when the exception was thrown. As you can see, we have travelled back in time to the point where this exception was thrown in the standard Java libraries. IntelliJ is decompiling this library for us to provide source code representation, and this would also work for other third-party libraries or classes for which we do not have the source code. Here we can see that the mod count does not equal the expected mod count for this array list. In order to determine when the mod count variable was changed, we can right-click on it and go to its implementation. Here we can add a data watch point, which will cause the execution to break when this value is modified. Let's use resume back again to run back in time to the point where this mod count value was changed. Again we have jumped back in time, this time stopping at the data watch point when the value was incremented. We have actually stopped where the value is still 20, as you can see in the variables window in the bottom right. We can use the usual forward step over this to see that value actually being incremented to 21. Notice as I step backwards and forwards in time, the variables in the variable window update. Think about what this means. I can go back to any line of code that was executed and see the complete program state. There is now nothing about my program's execution I cannot just see. If we look at the call stack frames on the left, we can see how we got to this point. And as we go up the call stack, we can find the point where the add method was called on the array list. In the application source code, we can see a mutator thread is adding an element to the array list without any concurrency protection. As the main thread of the application is currently iterating through the array list, modifying it is unsupported. This is obviously a canned example, but the whole process of following the effect back to cause and ultimately the root cause will work for real-world applications as well. I have been using the IntelliJ IDE Community Edition running on Windows, with the application running remotely on Linux. Time Travel Debug for Java can debug an application running under JVM 8, 11 or 16, and on any recent version of most major Linux distributions on x86, including in VMs, containers and in the cloud. Thank you for your time.